So this is the product. This is really the product of 5 years of research by the Exploring Ethical Decision-Making Engineering team. My colleagues are Trevor Harding at California Polytechnic at San Luis Obispo, University of Michigan, Carnegie Mellon, and everyone on the bottom there, those are all the graduate students who obviously do a lot of work. So the core issue of this presentation is whether or not ethical thought and behavior is an important part of being a professional engineer. And obviously, we believe the answer is yes, otherwise we wouldn't have had a 5-year grant from the National Science Foundation to study this. So if you look at the national outcomes for engineering education, the number one is really go ahead, please. The number one is ABET, right? An understanding of professional and ethical responsibility. And I've gone to ABET and made this presentation and basically said that's a ridiculously low bar. ABET has set the bar so low that you can basically meet ABET standards by having a guest lecture once in a 4-year undergraduate curriculum, which is just really pathetic when you think about it. If you look at the American Competes Act, basically that's responsible conduct of research, but anybody who has NSF funding has to include ethical training. That's kind of the basic of that. National Academy of Engineers, there's been a variety of reports that came out in the early 2000s by the NAE and National Academy of Sciences that really talk about high ethical standards and professionalism. And the gist of all of these reports effectively is, with technology and globalization and the rapid things that are happening, that the students aren't really equipped with the ethical thought that they need. So the technology is kind of outpacing our ability to consider that technology. We can do something, but should we? Is really what a lot of these reports say. And so that the students really need this high ethical standards because they need to ask the right questions on whether or not they should be doing some of the things they're capable of doing. And of course, every society has some sort of professional code of ethics, so it's just going to leave it at that. So this is our framework. Our framework for professional ethics is effectively ethical codes. I think you can do one more, and there's going to be an animation, right? Ethical codes is basically prescriptive decision making. You're going to do something because I tell you to. The code says I should do it, so I should do it. Professional ethics is actually starting to use your own framework of logically figuring things out. And then socio-moral ethics is that's autonomous decision making. I'm going to make the right choices because it's the right thing to do, not because anyone else tells me to do it. That's kind of a framework for professional ethics. So ABET is down here. Then you've got, this ethical codes, and then you've got, okay, are we making the right ethical decisions because it's the right thing to do for society? So what is our DECEIVE project? I'm going to go through this pretty quickly, because we do only have 10 minutes. This is up here just to show you we have a model. We actually have a model for how we've analyzed this. Students come in with characteristics. This is the college experience. That college experience includes institutional culture, as well as the peer culture. Inside the peer, so you have hundreds and hundreds of peers, is an individual student. And that individual student has formal and informal curricular and co-curricular experiences. What comes out is ethical development. And the ethical development has 3 parts. Knowledge of ethics, ethical reasoning, ethical behavior. What is my knowledge of the code? Can I reason through a dilemma? And how do I behave after I reason through that dilemma? We had 18 diverse partner institutions. We surveyed over 4,000 engineering undergraduates. We invited over 20,000 to participate. This represents 15% of all engineering undergraduates in the United States that given year. So the point of this is really, this is an unprecedented study. There's no other data set that exists on this level. Our phase 1 was going to those 18 institutions and doing focus groups. Then we had our online survey. And then we had regional meetings to just basically disperse this information back to our partners. This is our group. That's what I was saying. These institutions account for 14% of the engineering baccalaureate degrees awarded in the U.S. So from bachelor's, we have, oh, and by the way, all of this is IRB, and all these institutions signed up so that we could tell their names. So this was released. They have all agreed that we could release their names. So you can kind of see Penn State, Purdue, Michigan, and then all the way down to Bucknell, Cooper Union, Ohio Northern. So how do we measure ethical development? Keep going. Again, ethical reasoning, ethical behavior, and knowledge of ethics. We looked at all 3. So knowledge of ethics, we used FE-style questions. The National Collegiate NCES basically did not allow us to use their questions. Longer story. So we used FE-style questions. What we did is we contracted with a couple publishers of books on FE reviews and used their questions. So these are basically review manual type questions. So just to give you an idea, what is the best word for this sentence? Health, wealth, safety, and welfare. And then questions about reputation. So without going into all the detail, we had 5 questions on the survey. This is the percent of students that got it right. This is increasing complexity. So 70% of students got question 1 right, which was the health, safety, and welfare of the public. And then 58% of students got the one on reputation right. Okay, so this kind of gives you an idea. This was, if you look at the 5 total questions, and this was great. This is really, really great. If you're doing research, survey research, you love normal distributions because that means you can actually tell something. If everyone gets all 5 right or everyone gets all 0 right, you don't know anything. And so the interesting thing about this was, this is just an anecdote, but my graduate students in moral philosophy took this and got all 5 questions right. And they said, this is going to be the silliest survey ever because everyone's going to get all these right. Engineering undergraduates perfectly normally distributed. So 31% basically got 3 questions out of 5 right. So this is actually what we want because we want to be able to tell, well, why did they get 5 or 4 right and why did they get 1 or 2 right. Ethical reasoning. Basically use Kohlberg's theory of moral development. Personal interest versus universal ethical principles. Just to give you an idea what this means. Pre-conventional is like kindergarten. I do it because I do it for me. Okay? This is, Mahatma Gandhi, Mother Teresa. It's all about the social good. Everyone else kind of falls in the middle, which is you kind of obey laws and social norms, but it's not because you think it's the right thing to do. It's kind of, well, this is the way society expects me to behave. Okay? Go on. Keep going. I know we're running out of time. So, again, prescriptive decision-making, ethical codes, autonomous decision-making. This is what really Kohlberg's model is getting at. So we measure that using the DIT-2, the Define These Issues test. This is a very good, well-established, validated model. We didn't want to reinvent the wheel. What I'm going to tell you is that the primary measure is the N2 score. And the N2 score provides an indication to which extent an individual uses principled decision-making. Okay? So a low N2 score means that you're kind of like a kindergartner. I'm doing it because it's all about me. A high N2 score means you're doing it because it's about the greater social good. Okay, so this just gives you an idea. So that's your personal interest score, that's your maintaining norms score, that's your autonomous decision-making score. A weighted formula gives you an N2 score. What this means is this bar right here is college-age students. So this is like 2 standard deviations of college-age students. That's engineering students. Okay, you want to be high, not low. So not only are our students below national norms, they're on the low end. Engineering students are on the low end of college students when it comes to that. So you want this to be higher, and you want this to be lower. So basically, engineering students have lower levels of moral decision-making capabilities than their peers in other colleges. That's how you can interpret this. Ethical behavior, academic dishonesty in college. Just to give you an idea, when you look at all the literature that's out there, career orientation versus levels of cheating. So this is basically an authentic measurement of ethical behavior. Do I cheat or do I not cheat? Okay. Philosophy, arts, and languages. Physical sciences, natural sciences, social sciences. Business, engineering, medicine, and teacher. So the more career-oriented the profession, the more you cheat. There's going to be one more bullet that pops up. Between 60% and 90% of engineering undergrads engage in some form of academic dishonesty, depending upon the study that was done, and depending upon how it was defined as academic dishonesty. But in a nutshell, engineering undergraduates cheat way more than their peers. And there's multiple reasons for that. It's not only the student body, but it's also the effect of the curriculum and what the end goal is. And the only good thing about this, the only one who cheats more than engineering students are business students. This is actually in order. And after engineering students are medicine students. So think about that. Medicine students cheat only after engineers and business students. So that's actually in order. And the humanities and languages cheat the least. So this is just kind of a little fun thing here. So everyone says, well, that's because of the students who come to engineering. Well, this is actually looking at cheating behavior in high school versus college. All right, and humanities majors versus engineering majors. The way you can interpret this is, they come out of high school the same. The ones in humanities develop a moral code along the way, and the ones in engineering don't. Okay? So this is, we looked at pro-social and anti-social. Remember ethical behavior. Pro-social is basically volunteering, doing things for the good of the campus. Anti-social, we more or less did cheating, and we also talked a little bit about work. Okay. Just to give you an idea of some of the numbers, basically 69% of all engineering students engage in at least one pro-social behavior. And so you kind of look at what you're talking about there. But again, we're talking over 4,000 engineering students at 18 universities, all right? And so about 60% of them participated in at least one volunteer service project. And then this is the other side of it, right? 24% cheated on tests, 45% cheated on homework assignments, 64% knew about cheating and didn't report it, etc. Okay, keep going. We also looked at curricular experiences. There's two parts of this. Where did I receive the curriculum and how was it taught? So this is location, this is pedagogy. Okay? Was it in a capstone or was it in a skit? You know, did I see a skit in a capstone? Then I would mark that, and I would mark that. The important part here is what I call the donut effect. This was probably one of our biggest findings. We asked the students, what is the most influential thing that you get? The freshmen have a whole bunch of things. These arrows means that the juniors reported the exact same things as this freshman. So the idea behind this, the way you can interpret this chart, is that the students get quote-unquote meaningful and influential ethical experience as freshmen, and they don't get it again until they're seniors. And even a lot of the seniors said, wow, the only time I talked about ethics was when I was a freshman. So you have nothing in the middle and only a few things in the senior year. So the conclusions of the study, I didn't present you all the data because, I mean, this is just ridiculous volumes of data. But in conclusion, institutional culture played a role on how students behaved and articulated concepts of ethics. Out of those 18 schools, we went to some places that were just sad, dreadful places to be a student. Curricular quality, more important than quantity. There was an inverse relationship. If you give them too many ethical experiences, it actually didn't help. It was all about quality, not quantity, when it came to teaching them in the classroom. Co-curricular, students who were involved were more reflective on ethical decisions, more articulate, and actually had a better ethical code, except the ones that got over-involved became more unethical. So there's that inverse curve. You got too busy and then you start cheating because you just had to cope. Satisfaction, there was this was a good one. Inverse relationship between reasoning and satisfaction. Students with higher reasoning were less satisfied with what their teachers were doing. And the last couple point, there's little correlation between ethical behavior and reasoning or knowledge. What this really tells you is, I can regurgitate the code to you and get a 5 out of 5 on the FE score and have no ability to reason ethically and have no ability to be an ethical person. They can study for the test. And there's little awareness by all participants. I know, come on, stand up, stand up. There's very little awareness by all participants that ethics was a developmental issue. We would not teach advanced structures before mechanics materials, before statics, before physics. Yet we believe that as freshmen they can do these advanced ethical problems. You need to treat ethics like a developmental issue because the 23-year-olds are at a different place than the 18-year-olds. And nobody seemed to really think of it that way. So, and that's it. Thank you.
Is a snapshot of an ongoing project. This is not the conclusion of the project, and all I'm going to be talking about is one part of the project. So it's just too vast and there's too much to really cover in a 10 to 15 minute presentation. But the project itself was initiated by DTE Energy. They came to Lawrence Tech. They asked me to head this project up. It's an energy assessment and savings at the Michigan Agricultural Commodities Facility. I just call it the MAC, MAC here, facility in Marlette, Michigan. And so we started this last summer, and we've been working on it now through last fall, this spring, and we'll go through into probably the middle to the latter part of the summer this year. Many of you probably don't know where Marlette is located. It's a very small town, has one stoplight. It's located right here. This dot is about 10,000 times bigger than the city in relationship to the map. It's a very small town. I've driven through Marlette several times and I didn't even know I drove through it. So that shows you what's going on. This is this is supposed to be a color. That's not a very good color photo. This is an aerial shot of the MAC facilities. They have a rail spur that comes through, and these big circular devices here are grain storage bins. And so what we're doing is we're looking at how they convey grain, move grain in and out, and also these bins have big, large fans that dry the grain to keep it dry, because if the grain gets wet, it will get moldy and mildewy and there's other problems with the grain. So what we've been doing is we've been coming up to this facility and doing a series of energy studies. And this is just to give you a sense of the scale and the size of these facilities. Each one of these bins holds approximately 300,000 bushels of grain, which is about, depending on the grain, if it's soybeans or wheat, could be anywhere from $2 to $6 million worth of grain in each one of these bins. So they're large bins, large facilities, and you'll see overhead distribution conveyor systems. This is a receiving leg where the grain gets dropped down from the back of a truck into a graded device here. These things open up, they dump the grain in here, and then there's a lift that lifts the grain way up 250 feet up into the air, and these side tube devices gravity feed the grain to wherever they want it to go. These are examples here. This is one of the conveyors. This is from a train receiving station. This is a temporary storage bin where they dump the grain, and there's a conveyor here. This set of basket-looking type devices is on a conveyor belt, and that's located in this large receiving leg here. So they push the grain through an auger over to this receiving system, and it lifts this up through these baskets all the way up, and then it dumps it to where you want to go. Again, more pictures. This is inside in one of these large storage bins, just to give you a sense of how big it is. These are 3 students. This is San Wong, this is Janet Coggins and Jake Ball, and this is Dwayne Geiger. This is inside. This is a 400,000 bushel storage bin. So these things are monster, and it's very interesting. The acoustics in them are really fun. You can do all sorts of fun things. There's holes in the floor to move the grain in and out. This is another example of large storage bins, large conveyors here, and here you can see right here there's a vent fan. This is a temporary storage pile. There's 400,000 bushels of grain right there. That's worth about $4 million, that pile of grain, and it has these tarpaulins on it. And the way they keep the grain dry is they put these tarpaulins on it. There's these fans all the way around. They suck the air out of this temporary storage bins to hold the tarpaulin in place. We were supposed to go up there this past week to do some more data collection, and they had a bunch of winds and blew their tarpaulins off. So they said, no, you can't come up this week. No work this week. Again, just some examples, but I want to focus a little bit more. This is the primary receiving leg that we've been studying a lot. We've done a lot of work. It looks like a garage door right here. That's where the trucks come in, and this is a photograph of them dumping the grain. This is soybeans they're dumping here, and these trucks come in and they dump huge quantities of grain. So they're moving literally tons and tons of grain at a time. This is a real materials logistics process that they're looking at. Here's an example of the large 50 horsepower fan dryer fans. There's 4 of them all the way around the perimeter of these very large silos. Again, pictures here, and this is a 10 horsepower fan for a temporary storage. They have 2 primary sources of energy consumption. These fans, these drying fans, and then these conveyors. They all have motors. So what we're interested in is we're interested in understanding how they manage the energy of the motors. And what I'm going to talk to you today about is essentially data relating to just the fans. So here's one of their 5 meters at the Marlette facility. These are the data for their energy usage. For one of the meters, it's meter 9413322. This 1 meter used almost $73,000 worth of electrical power in 1 year, over a course of a 1-year period. They have 5 of these meters. So they're running typically somewhere between $450,000 and $600,000 a year in energy usage. So there's a real benefit to having a chance to get and improve this. And the main reason is, remember what they're dealing with. They're dealing with commodities. If their operating prices go up, they don't get to raise the price. The commodity price is set by the options board in Chicago. So if they want to make money, they have to get their costs, their operating costs down, and that's the only way they can do it. So this is one of the reasons they're interested. This meter is for this data set. It's that one right by the garage door where they come in and dump the grain. So they have 5 sets of meters, and this is just one of them. How are we looking at helping them? One of the first things we're doing is we're doing a variable frequency drive, VFD studies with them. And this is an example of actually one of the meters that we're using. It's a Altivar variable frequency drive. And what the nice thing about variable frequency drives is they regulate the operation of the motor. And how they do that is, instead of having a pure sine wave power output 3-phase, what they do is they do a pulse width modulation where they can regulate the power going to the motor through a series of positive digital pulses and negative digital pulses. And the way they do that is through some instrumentation electronics in the variable frequency drive. And so what happens is they simulate a sine wave going to the motor with these pulses. And by doing that, they can more accurately regulate the energy going to the motor and set it up so that it's much more efficient operation. So one of the things that we did is we purchased 5 of these meters. These are, I'll tell you, these are dandy pieces of hardware. They're fluke meters. They're 435 twos. And these things do everything but wash your clothes and put gas in your car. They do amazing stuff for almost everything that you want to measure electrically. They're normally about, this plug for Lawrence Tech. These mini meters normally run about $9,000, and we contacted a company in New Jersey that looked like they might have a good price on them. And so we were talking to him, one of the students, he says, oh, I go to Lawrence Tech. And he goes, oh, you go to Lawrence Tech? I went to Lawrence Tech 35 years ago. I'll give you guys the wholesale price. So we bought these for $6,000 a piece instead of $9,000, which is kind of, so we were actually able to buy an extra meter. So what we did is we got a fan. This is a 10 horsepower fan. We set it up here at Lawrence Tech. We built a mounting system. We were able to put obstructions across the fan to load the fan and not load the fan. This is one of the tests that we did. And we set up variable frequency. We bought a variable frequency drive. We set up the fluke meter. And so we could plug and unplug with the variable frequency drive or without it and run the fan. And this is just a quick snapshot of data here. What you're looking at is 2 data sets. On this side is volts RMS. This is for just this is for all 3 legs, so we're monitoring voltage. So here's voltage across the top, and over here is RMS current. And so what you can see here is a set of data. This is turning the fan, that 10 horsepower fan on. We spike all the way up to 300 amps for a period of about 2.5 seconds or so. There's 2 seconds, and then we come down to a nominal operation. And then this is with the VFD. So we've been able to completely eliminate this spike. This is voltage dropping after the VFD was turned off, so don't worry too much about that. But the VFD eliminated this huge power spike, and you'll get appreciation for what that means when I tell you how many fans they have at the Marlette facility. This is just a quick snapshot. We did various tests with the 10 horsepower fan with obstruction across the outlet of the fan, fully open and then fully obstructed. And this is the active peak power that we were monitoring with and without the VFD. Typically, we brought the power, the watts down to about 7,000 watts versus 81,000 watts. So we were making some big headway just with the VFD. Very important work, and that's pretty typical all the way through all the data. Then we got a 50 horsepower fan here on campus. This is an example of the drying fan. We set it up at the ARC building in North Campus. We built our own mounting frame and bolted it to the safety barricade posts up by the cooling fan system for the air conditioning system up at the ARC. We used the variable frequency drive on the wind tunnel fan up in the ARC, and this is Eric Onan and Michael Abramson, who are doing some work. We put another obstruction across the outlet of the fan, and we hooked it all up, got it running, and we were able to monitor pressure. We have another data acquisition system here. And so we did a series of tests here to get an understanding of how the operation was, how we could best operate the system. And then we went up to the MAC facility in Marlette, and here we are. We were out in the snow all day. It was a nice, cold, 15-degree day that we were out there, and it was snowing like crazy. This is the power shed for the data collection, and so here's a quick snapshot of some of the data. This is, again, a 50 horsepower fan. This is only one leg, one phase. There's 3 phases, so you multiply all these numbers by 3. And so what we have here is, without the VFD, we're going up to 425 amps for a period of about 5 to 6 seconds. And then these are data at different ramp rates with the VFD. And so it turns out that we think probably about a 20-second ramp rate with the VFD is going to be a reasonable operating number. And what we're interested in doing is knowing what the area of this is, because if we can find that area, we can find out how much energy we're actually saving the facility. So turns out, just this is one of my last slides here, that green area has a certain number of coulombs. You're essentially counting electrons. And from here, we can say, okay, with the VFD and without the VFD. Without the VFD, just to turn the fan on, just to go click, turn it on, costs them 7.2 cents per turning the fan on. Without the with the VFD, we knock that down to about 3.4 cents. So just by turning that fan on, it's 7 seconds a fan. So just to wrap up here, I still have 2 seconds? Okay, I thought you were ready to give me the shepherd's crook. Get that guy out of here, get the next speaker. Okay, I just want to walk you through a couple of pieces of information. They have 16 bins at Marlette. Each bin has 4 fans. They typically turn on each fan 100 times a month. So you have 400 starts per bin. And so I've got the numbers here. They have 8 facilities at the MAC, operations centers. Just to turn the fans on, $44,165 a year, just to turn the fan on. That's not the operating cost. And with the VFDs, we can help them save $35,800 a year just in turning the fans on. That's just the fans. Now we've got all the other motors. They have 300 motors at this facility, and multiply that by 8. So the question is, can we help them? And the answer is, you bet we can. And they are just jumping hands, and they're just like, when I was going through the data, they were just ecstatic. Because they're looking at this money is just going right out the door. The other thing is DTE is very interested in this, because imagine turning 16 times 4 fans on all at the same time, which they do fairly frequently. They'll turn them on all over the course of a period of about 1 minute. That's a huge power surge from the grid. DTE doesn't like that, because all the lights in Marlette go dim for 20 seconds, and I'm not kidding. So the savings is astronomical money-wise. The savings is astronomical as far as DTE's demand goes. They're right at the end of DTE's service leg. And so they're very concerned about having enough power to do the things. They're expanding. They're going to be putting in 2 more bins. So anyway, that's the benefit of all of this. Yes.
The other end of that equation, what does it cost to install a VFD?
The VFDs are variable costs. If you buy multiples, it's cheaper. But typically, they run somewhere on the order of $800 to about $4,000, depending on the power settings. So you can get
return investment's really quick.
They're estimating the return investment is somewhere between 14 and 18 months. So it's sizable, and that's just with the fans. And we feel we can go across the board. We are conservatively estimating we know the utility costs are about $5 million a year. We feel we can save about $1 million a year.
And then you have the other facilities in Michigan.
Yeah. And so this is really, really interesting. A lot of farmers are very interested in this.
Well, thank you very much, Robert.
All right, thank you. So I'm going to talk about enhancing Michigan climate database for mechanistic empirical pavement designs. So when you talk about pavement designs, so this is a new method of designing pavement. It just came out in the last few years. All this time we were designing pavements with the road test done in 1960s. That's why you can see all these pavements are crumbling, because we didn't have good method of designing pavements until this time. All this time we didn't consider a effect of climate in designing pavements. Not much. It counted a little bit, but not much. But at this time, in the new design guide, there's a whole climate model to incorporate the material behavior into the pavement design. This was funded by Lawrence Tech faculty seed grant. Just started in January, and it's an ongoing project. So I'm just going to present you the very preliminary test results. I want to acknowledge my co-authors, Susan Hansen, she's a adjunct faculty at Civil Engineering Department, and Kim Kleber is a civil engineering student. She's working on this project. Unfortunately, nobody's here today. Introduction. So environmental conditions, as we know, is a major impact on pavement performance. This includes precipitation, temperature, freeze-thaw cycles, etc. So you see in springtime, all these potholes are coming up. That is due to the environmental conditions. So spring thawing of underlying materials. So new AASHTO, Mechanistic Empirical Pavement Design Guide, included, as I said, a climate model. It's called Enhanced Integrated Climate Model, or EICM. So basically, EICM predicts the changes in pavement layer properties due to climatic effects. So it basically predicts the moduli of different material in different times of the year. So summertime you have a fairly reasonable value, and then if it goes to winter time, so you have a high frozen subgrade and so on, right? And in springtime you have a very soft subgrade. So if you talk about subgrade. So that's what is EICM doing. So to do that, we need a good weather data. So this includes hourly values of air temperature, precipitation, wind speed, percent sunshine, and so on. So the new program requires at least 24 months of data. The location of the pavement is specified latitude and longitude. And then the program can select the closest weather stations to get this weather data. When you talk about Michigan, they included only 19 weather stations in Michigan. So most of these weather stations are located in lower half of Michigan. For example, there's a map here. When you talk about Upper Peninsula, we have only 3 locations for all this area, right? So as you know, when you go to closer to water, so you have a different weather map. It's basically different climatic zone. And if you take here, it's totally different from this area. So we are not really considering correct weather patterns to design this pavement if we use this included data. So as I said, so only 3 stations in Upper Peninsula. If you take a middle part of this Upper Peninsula, these are all about 100 miles from each of these weather stations. So that could make a difference. We don't know it. So we have to think, is there an effect on that? So that's the question. This data has approximately 10 years of data. So our question is included data sufficient to characterize Michigan weather patterns? So that's what we are going to see. Also, can we expand this data to include more weather stations or more data? It has only 10 years of data. Can we expand to include more data, 30 to 40 years of data? So this is the existing data. And also another thing we noticed when we plot this weather data, the location information given in latitude and longitude, what they did was normally this latitude and longitude has if it is in decimal degrees, you have at least 6 significant numbers. What they did was they cut into 2. So due to that, there's a location error when you plot into a right scale. So for example, in this case, it's 11 miles difference. And this one actually, correct, if you plot their location, it is in Wisconsin, not in Michigan. So there are so many errors, and this one is in Ohio. It's supposed to be in Michigan, in Adrian County Airport, but now it is in Ohio. So there are so many errors, so we have to first correct those things. And now we have to see whether this data is enough to characterize the Michigan weather patterns. So first of all, we took those 19 weather stations and so one of the errors we found was the spatial errors of 9 to 31 miles based on that latitude and longitude error. So, and also we looked at, there are so many missing data inside that 10 years of data. This includes temperature data, wind speed data, and so on. So most of the data included this. 24% of the data, actually daily minimum and maximum temperatures were not included in the existing data. So our question is this, now we have enough data or not? So what we did was we took a one pavement section and select 3 weather stations in Metro Detroit area. Okay? They are very close locations. One is in Metro Airport, other one is Willow Run, other one is Detroit City. They're like in 20-mile distance. And then we ran the program for these 2 pavement sections, 9-inch concrete pavement and a 9.5-inch asphalt section. Just to see whether this 20-mile difference make a big difference in pavement performance. So this is the, for concrete pavement, one of the distresses is the faulting. Faulting is the difference between the slab elevation between joints. So that's what you see when you go on a concrete pavement, you see that's due to faulting, right? So when you look at that data, in 20 years, so this is predicting, these are the 3 weather stations, everything was same, only the weather stations were the difference. So it makes a difference in after 20 years, it makes a slight difference in performance, in faulting. So this is another distress pattern that's cracking. When you look at the 3 weather stations, you will see this is a Willow Run, shows about 6.5% cracking versus this shows only 1% cracking. So as we see, why is this difference? I mean, this could be the error in the data. I mean, you wouldn't expect these weather patterns in these 3 weather stations should be much different, right? I mean, Willow Run versus Detroit City, they are like 20 miles apart. You should have the same temperature pattern and so on. But still, there is a big error in predictions. So this is IRI value, that's International Roughness Index, that's the roughness of the road basically. And these are the asphalt pavement results. The rutting, you'll see still there is a difference. IRI probably went into the same area. So observations. So we need to update the climate database, the location information. And the pavement performance predicted by these 3 locations, we saw there's a difference. This could be due to errors or insufficient data items. Maybe there is some errors in Detroit Metro Airport, maybe have good set of data versus other 2 weather stations. That could be the reason. So we need to dig down those weather data and see what's there. And also, we can see more weather data will increase the reliability and accuracy of performance, these prediction results. So how can we update this climate data? So if you look at the NOAA website, National Oceanic and Atmospheric Administration, it has 238 weather stations in Michigan. They only use 19. So you can really expand this weather data. So these are the weather data, NCDC weather data. Instead of 3, there are so many weather data in Upper Peninsula, you can see. And also, National Weather Service has 992 stations in Michigan. So if we can combine these 2 into a huge database, we can have about 20 times more data for pavement design in the future. So we can combine all this data, so there will be a lot of spatial coverage, not like 3 stations in this area, and so on. So future tasks of this project, so we're going to gather a sample of weather data from NCDC and National Weather Service and create a database in EICM format, and then compare the pavement's performance by comparing the included data in the program versus newly created data. So that's the next task. And also we're going to do a quality check of the collected data. The other thing is, if you have missing some areas, we can develop an interpolation technique to have, if you want to have somewhere here, we can take these 5 locations and create a virtual weather station somewhere here. So that's something we are looking at too. That's where this GIS come into play. ArcGIS software has a tool called Natural Neighbor Interpolation. So you take a sample of data around it, and you can create a new data set using interpolation technique. So those are the future tasks. So that's about it. Thank you.
Thank you, Ray.
Thank you. Good morning. I am currently enrolled in the Mechatronic Systems engineering program here at Lawrence Tech, and this is my thesis for the network. The title of that is Equivalent Circuit Modeling of Lithium Iron Phosphorus Phosphate High Current Charge Dynamics. My main advisor is Dr. Fletcher. The other people on the thesis board are Dr. Olivier, Dr. Chris Riddell, and Zach Lott from the people network. Okay. First slide, the technological challenges of implementing lithium-ion batteries. So a little bit of background here. Safety, of course, prevalent in everything. There's weight, cost, but the issues that I'll be focusing on are life cycle range, which is energy density, and the charge-discharge rate, which is power density. So these are the dynamic characteristics to the batteries. Pictured is the Nissan Leaf, which is a pure EV, and the Nissan Leaf instrument cluster, where we try and convey some of the information going on with the systems in this electric vehicle to the driver. So you see the charge indicator, which is what you would normally have as a fuel indicator in the vehicle. So what are some of the important variables? What are some of the important metrics when it comes to the, so you have a number of different graphs here. This is supplied by A123. This is the low temperature discharge performance, discharge characteristics at a specific temperature, and life cycle performance with 100% depth of discharge, meaning that it's fully discharged and fully charged for various number of cycles going out to 1,000 here. Here you see the differences between temperatures and currents at which they're discharged at, and the voltage that they indicate as they're being discharged. So you see the thermal dependence here. Here you keep the temperature constant, but you're varying the discharge current. And so this is purely current dependent voltage characteristics. And here you see the amount of energy available as you do these 100% depth of discharge cycles up to 1,000 at various temperatures and current ratings. And so this is trying to show you that if you stress the cell heavily, if you're doing large amounts of current for discharge and charge, and you're introducing it to extreme temperatures, the amount of energy that the battery is capable of storing decreases over time. These are the particular cells that I'm testing with. These are A123 cells. The chemistry, as I said before, is lithium iron phosphate oxide. These are some of the metrics involved. So it's 2.3 amp hours with a standard voltage of 3.3 volts. It's capable of a continuous discharge of 70 amps, maximum discharge of 120 amps for 10 seconds. They have recommended current ratings that you're supposed to follow if you're implementing this in something like an electric vehicle or a power tool or something like that. The testing that I'm doing is surpassing these recommendations in order to get an understanding of the dynamic behavior that is good in there. And then there's also the operating temperatures that they're supposed to come at and the amount of cycles that they're rated for. This is the experimental setup. So this is in E18, the Alternative Energy Laboratory. Just the power supply here. I have loads here. The batteries, I actually have on a mounting here that's not in the picture. There's the data acquisition system and the computer that's hooked up to. So it's all about being able to supply power, controlling the current and voltage, absorb power, controlling the current and voltage, and data acquisition, and then the data analysis. There's a diagram of that setup. Like I said, there's the power supply and electronic load that I can switch between. There is the cell measuring voltage across that. There is a shunt that I'm measuring voltage across to calculate current. There's the temperature of the cell, and then there's an ambient temperature. Here's an example of the data. This is at a 1C charge. The C rating is common in the industry. And what you take is the amp hour rating of the cell, and you divide by the amount of time in hours which you're discharging or charging, and you have the C rating which you're discharging or charging that cell at. So it's kind of a normalized way of showing that current. The 4 different metrics I have on here is the battery voltage. So throughout the charge profile, what the voltage is at. This is the current that I'm charging at. The red is the ambient temperature, and the green is the cell temperature. So here, 1C charge, I'm maintaining a constant current, and it's the voltage dynamics maintaining that charge current that I'm interested in observing. This is kind of a typical plateau that you'll see when you're dealing with the lithium-ion chemistry. So you get an initial jump. You're starting from a completely discharged state here. You have an initial jump. You have a nice plateau of continuous voltage as you're charging that, and it's very similar on the discharge path too. That's one of the benefits of lithium-ion, is they're very consistent when you're going through these charge-discharge cycles for a good portion of their energy life. Then as you approach the maximum charge, they start to increase sharply, where I cut the voltage off at 4.2 approximately. Here's an increase to 6C, and you start to see some differences in the way that that voltage dynamic portrays itself. It's still pretty similar, and you also see that temperature rises quite drastically. Jumping to 12C, you start to see a major difference in the initial voltage dynamics, where you get this increase, and then it decreases down to that plateau region before it increases to its final charge portion. Now, there are a lot of analytical methods to showing how these batteries behave, depending on a lot of different variables that are very computationally complex. So for the chemists involved with developing these cells, they have models that are necessary to predict performance, but it requires a lot of processing power and a lot of memory. The computers involved in this are generally very complex, and so to get this information onto a platform like a vehicle, where you don't have that processing power, you don't have the memory capabilities, you need to start looking at empirical models. You can't rely on these analytical methods. One of the popular options of trying to get that information onto something that's not as robust is the equivalent circuit model, where you take a simple RC circuit and you model the resistive and conductive, capacitive elements so that they emulate, so that they look like what that voltage dynamic does, depending on whatever variables you want, whether it's current, temperature, SOC, to make it look like these voltage curves. Now in the literature, when it comes to these equivalent circuit models, a lot of them focus on low charge, low C units. So you're looking at 1C, 2C maybe maximum. But with cells like the cell in this presentation, and applications like electrifying vehicles, you have high current dynamics, and these models don't necessarily portray some of these phenomena that we observe here. And so to cover that, I've added an inductive portion into this first RC portion of the circuit to help state what happens when we have these high charge instances. So this is an example of the equivalent circuit model that is being used in this approach with this inductive element added. This is the equivalent circuit model in the Simulink SimScape environment that I developed to do the regressive analysis to find how these variables fit into the data that I took, or the data that I measured. This is an example of some of those parameter values that were obtained through that regressive analysis. So here you see the R1 value and the L1 value. Going back, this is R1, this is L1. R1 indicates some of that initial jump that you get during the charge and discharge methodology. The inductance is put in there to capture this initial hump, so you have that resistance to current flow that helps portray that initial high voltage that decreases as time goes on. And then you have the remainder of the RC components. That's kind of the standard equivalent circuit modeling to show the rest of the dynamics. So once I have these values taken during the different C rates, so this is starting at a low, this is going to 1C, 212C, 1C, 212C, I can come up with these equations, feed them into that model, and then depending on the current that's seen, I can accurately predict what the voltage is going to be. Validation of this model. So here we have the measured data. This was on the test stand, what I was collecting, versus the curve fit for each portion, so for each charge cycle, 1C, 2C, so on. I then take that curve fit, do the regression analysis, get fixed variables for each C rating, and then I'm able to compare the fixed variable portion, so that 1C, 2C, 12C, the variables that come of that, and then to the equations that are developed and overlay that in order to understand what the error involved in is and where further analysis is needed. Well, this is just the beginning to the battery model. All of the dynamics here are current dependent. There's a lot of different variables that go into trying to understand what these cells are doing. Temperature being one of the major ones that isn't included. And SOC actually has a large role to play in how these dynamics represent themselves, depending on whether it's 0%, 50%, 100% state of charge. So the application of this, just to touch on this again, is for applications like vehicles where we don't have a lot of computational power to go along with these models to figure out what's going on, because it's important for every component in these systems to understand what's going on with the battery, how much energy you have left, what the life cycle is. We want to simplify those models and put them into applications like vehicles for SOC and SOH algorithm development. So, thank you. If you have any questions.
I'm assuming that the C rating and the temperatures are linked in somehow, right?
Absolutely.
So then how are you going to be able to decouple that in terms of doing your models?
The model needs to have all of these different variables in it, but this is just the beginning of development of this model. So this is for a master's level thesis, and there's a lot of work in developing an entire battery model. So I'm focusing just on the current dependent aspects of this, but later on we intend to integrate the thermal dependencies and the SOC dependencies.
So then the thermal dependency, you are going to have to use more resistors to change. Is the number of components that is changing, or is the value of the components that is going to change?
There will be, you'll have a temperature coefficient almost, so you'll have something on the side that will vary all of those R1, L1, C1 components as
So it's another component.
So,
Okay.
yeah, another component that those beginning components are dependent on.
Right.
So,
Okay.
My paper is on modeling and simulation of automotive energy subassembly for production improvement. Now, I've been in the auto industry for the last 10 to 15 years, and I came to Lawrence Tech, and with the experience I have and with Dr. Ali's mentoring, we were going to present this paper at the conference of engineering. Let me see which one I'm going here. Oh, I went the wrong one. There we go. We sent out the application with our abstract, and we did get accepted for the conference in San Juan, Puerto Rico this May. And simulation basically is trying to find out where we have issues in making this engine and trying to improve it so we can make our quotas up by improving on machine cycle times and throughput processes. Okay, so our target is to increase production and also objective to analyze the potential bottlenecks. What a bottleneck is where we're not making correct production, and so we try to increase it, so or try to modify our manufacturing process to improve it. This is the engine that this head comes from. This is a head assembly, and the simulation was to follow the process. This is a process how to make this head sub-assembly and how to improve the times how to make it. This is a 4.7 liter engine, okay, and the head sub-assembly is right in here. And if you know anything about engines, this is basically what starts and cranks your engine. This is, that camshaft is connected to the crankshaft through a piston, and basically it starts the combustion of the engine by rotating. So the major subassemblies of an engine are called 5 C's. One is the crankshaft, which I don't have here. Another is a camshaft. This is a camshaft right here. Cylinder block is a block of the engine. And of course, what I was looking into was the cylinder heads. The goal of simulation is to mimic the real world simulation. Okay, objectives, again, to improve our throughput, identify bottlenecks, and look at utilization. And we do come up with a formulation, something called WIP. If in manufacturing, which is called, you always look at the WIP, which is your work in progress, which is your throughput times, your cycle time. So as we go through the simulation, that's why we're trying to see how our cycle times and throughput is doing. And this is the model that we're going to be simulating. It has 17 processing stations, 2 repair loops, and 20 transfers. What a transfer is basically a conveyor, continuous conveyor going through all the stations. And each station has a certain cycle time, about 17.3 seconds, to do a single task. Like at station number 2, this is what is done. It says intake valve. The intake valve is basically inserted into the head. There's intake valves are blue. The next step would be the exhaust valve, which is the green. And it goes on throughout the thing. And like I said, my presentation is probably 10 minutes, and in our process, we would have it head in 10 minutes as it goes through the 17 stations. Again, this is depicting the stations. This is part of the modeling system that we started. We're using a software called Arena. So you set up all the stations according to the task that's going to be done to build this head. Where do I get my information? There's a system called Factory Information System, and part of any simulation is to have good data. You have to have data to focus in and try to simulate how we go through the process flow at a certain time. Objectives, again, throughput determination, bottleneck detection. Again, when we're looking at production, we're looking at also optimization shift patterns and our manpower. This is how a graph showing the ramifications of when you have breakdowns in the system, the cost. It's quite considerable. So we're trying to minimize the breakdowns by detecting it through our simulations. You can't predict breakdown through the simulation. Again, in any process or simulation, you need input data, and we can look at machine time, gauging time, conveyor indexing time, everything that can be added to make the simulation more realistic. And this is where I get most of my data is through related data that comes through the plant at the moment. Again, you have your inputs, you have your simulation. Now what do we look at as our outputs? We're looking at our gross jobs per hour. We're looking at utilization. And a lot of times we're looking at the buffers and how, so we could rearrange our line to make our production. Again, these are some of the deliverables. Again, looking at our production, throughput, and overall. And one of the stations that we were looking at, station 6 left down in here, that was giving us readings that it was becoming a bottleneck. Right here is a slide showing the arena model itself, where you have to model the process just like in the process flow. And these little squiggly lines are the queue times. Queue times are basically you measure the time going through each station. And if we're waiting or not waiting, they're similar to any queuing system. Some of the deliveries, when you do the simulation, you start with 1 replication, 10, 20. You're trying to make the data look consistent, and then by doing replications, you find that after so many 30 times, the numbers start to balance out. The most notable result is the valve spring assembly, accumulated time. All right, again, it's all about production, is all about timing. So we spotted an issue right there. Part of the output deliverables, originally I had the equation of WIP, which is work in progress, and showing that from a certain amount of replication starting at 0 to 30, and the amounts we're having. But basically, if it comes out of this, is that we are spotting a bottleneck situation. Part of the station that I mentioned before, and right here in this graph, it's revealing that we are having most time is happening in station number 6, which that's saying that we're not manufacturing fast enough. We have to do something about it. In conclusion, the simulation results reveal potential head subassembly bottlenecks in station 6. Our queuing system is meaning that we're also have another potential bottleneck at the exit valve assembly station, which is station number 2. The average cycle time in the simulation was a little bit higher than in the real one, but in close range. So this is validating our simulation that in real time it's about 1945, and in our simulation is 23.81. As simulations go, if we get our values are similar to real time, we've done our job of putting real time data into use. Also, there's different p-values I'm going to show right here that's stating that part of our throughput and values that it's stating that 6 is a potential bottleneck. So the simulation worked. It was close to the data we had. Sad to say, this line that I did the simulation for made its last head yesterday. This is the 4.7 liter head for Mack engine. That's where I work in Chrysler. And our last head was made yesterday. if we have a new project in the plant. But the reason I got this one here was because the line was basically on its downslope and being discontinued, so I had the capability to read into all the data that they had there. So really there was not anything that I had to get excluded. So I had free reign of all the data and materials. All you see here is basically scrap materials. And again, this is what is put into the building of the head. We have spark plugs, we have springs, we have valve assemblies, we have rockers, but this is all put in this in assembly in 17.3 seconds, and our simulation said it was close to 23. So it wasn't, the validation of the simulation was verified. And as we go, again, this paper was going to be published in the conference, so it followed that we had to look at the different references and follow conference procedures on how we formulate it. And that's it.
Well, thank you.
Thank you.
Good morning.
Morning.
My name is David Ogbuaku, and I am a Davis student here at LTU. I'm here this morning to present to you on this inaugural research day a proposal of my dissertation. All right. I am very glad to have some of my advisors here. I have Dr. James Boyle, who is here with us. He's a technical specialist at Ford, where I work. And then Dr. Laura Laseki is my academic advisor. And the other distinguished professors you see here are members of my advisement committee. Background: the internal combustion engine, which operates the cars we drive, generates too much heat than it needs to convert fuel into energy. Okay? And for that engine to continue to perform as designed, the excess energy or excess heat that it generates must be cooled. Otherwise, it will not continue to perform. The radiator, the coolant, the pump, the cooling fan, thermostat, pressurized cap, the gas bottle, hoses, and clamps, these constitute the engine cooling system, and each serves a very important role to keep the system working as it should. The focus on this project is on the radiator. It occupies the largest space among all of them, and should be designed large enough to adequately cool the engine. Okay, here we see some depictions of the radiator. Okay, I think the important thing we need to take here is that the shape we see didn't change very much, but there are some configurations here. On this one, we see the end tank on the top and bottom of this model, and the size have the size are on the size of this. Whereas on this one, the end tanks are on the sides, whereas the top and bottom have the headers. Okay. One important fact is that since the late 70s, there has been a consistent trend towards lighter, leaner, and more powerful engines. Okay. And the material of construction has changed. The processing method has changed, and so have some design schemes. Used to be square. We see them more aerodynamic now. Okay. Also, brazed aluminum has replaced copper and brass as a preferred construction material for the radiator. Here is some schematic of how this works, the coolant flow in the automobile system. So I will animate it, but what you see is this, that the coolant flows from the lower side, from the hotter side of the engine towards the top, okay? And then from there, it goes to the radiator. From the radiator, it goes to the cooling pump, the water pump, which pumps it back to the system. So what you see is in the radiator, because of the air flowing through it, and then some other dependencies, the coolant, which is hot coming from the engine, is cooled at that point, and then goes to the water pump, which pumps it back to the engine to continue the process. Here is another trend that we see in the radiator design in the vehicle that we drive. This goes to buttress the fact I said earlier about the increase in power output of the engines we have. So this graph tells us that, say, a vehicle that is 2.5 liter engine, okay, in 1970 or so, we expected power output from that engine to be about 125 horsepower, okay? 2000, that same engine, size of engine, was outputting about 225 horsepower. So there is definitely increase all this along this time. And we know that the higher the output of the engine, the greater the cooling requirement. Because as it generates the power output, heat is involved. A lot more heat is generated in the process. So that engine has to be cooled if it must maintain its integrity. Here's another trend of the vehicles that we see. So we see here on this side is vehicles we used to drive or that used to be driven in the pre-1975 era, where they are big, V8s, big and huge. So they had large engine displacements, but they had smaller power outputs compared to what we have today. They have large engine compartment size and then large frontal area. So the practical result coming from there is that at all speeds, you had adequate cooling performance, all right? On the contrary, since the 2000, we have had cars, or we now have cars that are smaller. They are smaller, but the engine displacement is smaller, but then the output power is higher. They output a lot more power, but yet the space where they are packaged, including the engine compartment, is smaller. So even though we recognize that we need to cool them more, but then the space to package them is a problem. They are more aerodynamic in shape, so the practical result is that the cooling capability at low and moderate speeds is limited. It's not as much as we want them to be. So that brings us to the problem that we want to solve. We see two contrasting situations here: engine power output versus the cooling space. Okay, the higher the engine output, the greater the demand for cooling capacity. All right. Now, the greater cooling capacity, we could achieve that by enlarging the surface area of the radiator. We could do that. However, the desire to reduce weight has made us downsize the sizes of the vehicles. Therefore, even the car body has been downsized, so you don't really have the space you need to package the enlarged radiator that you require. So the objective of my applied research, therefore, is to find a solution to this cooling and packaging problem. Here's a representation of the radiator we had, or we now have, and what I'm proposing. Okay. As we saw earlier, they are rectangular, and then what I'm proposing is to have a conformal one. We see the shape change some, and we see how we could achieve that. As we progress in this, we want to take advantage of the aerodynamic shape of the vehicle, and then design, instead of a square or rectangular radiator, we design what we call a conformal radiator. So it will conform with the shape that we see of modern vehicles. And then that way we achieve the larger surface area that we need by utilizing the open space adjacent to and behind the headlight area of the engine compartment. How we would approach this is as follows. We investigate the formability of aluminum alloy, which is what we use today, the tubes, to find out how much we can bend them to conform to the shape that would give us an enlarged surface area. A device will be created to try to bend these tubes, okay, through various angles less than 90 degrees. Then we will use design of experiments methodology to examine the effects of the bend angles on the thickness of the tube, the coolant flow rate, the corrosion resistance. And then by that way, we establish the optimum bend angle as a result of the experiment. And we validate it, and then compare the design to existing practices to determine its applicability to production system.
All right, I have good one.
There's a reference I used for the increase in the power output of the engines. And that brings to the end of my presentation. And do you have any questions?
Do you have a question? Nope. So in your stage of your studies, as you are moving towards coming up with this solution for your radiator problem, what are your physical testing that you will be performing, if any, or is it all going to be simulation?
No, we will do some testing. As we bend the tube, we would want to know, introduce it to salt water to see any corrosive effect it might have, that the bending may have on it. So if we go back to this, we will see if the thickness of the tube has decreased, which would impact the flow of the coolant. We will see whether there's restrictions that would impact the flow, which ultimately would impede the performance of the radiator.
So in your overall design, you're going to be looking at a range of bends?
Yes, a range of angles. You can bend, I think you can bend up to 4 different angles and see what effect they have on the tube thickness and the other things, so that we determine from there what effect it would have on the cooling system.
Thank you very much.
Hey, good morning, everybody. How's everybody? Ladies and gentlemen. Sorry, and today's a good day to talk about concrete and water. However, specifically about storm water runoff and pervious concrete. So what are we going to do in the next 9 minutes and 5 seconds? Well, we're going to start to what is pervious concrete paving systems. What are those? Not just removal, right? Using pervious concrete paving system, which is our main topic of the ongoing research. This is an ongoing research that we are doing right now some preliminary results that we have, and then we're going to take a little of the status of the research and an update on the research. So let's take a look at the big picture first, okay? The effects of urbanization in runoff. I mean, whatever it is that the rains, what is going to happen with the water? Well, the water will deposit on the top of the surface, right? And eventually it will, the soil will get that water, okay, through infiltration, all right? Now, as we urbanize areas, what's going to happen with that water? Okay, imagine that we have just grass on that site, and then we have asphalt, we have pavement, like the previous presentation. So what's going to happen with the water that is going to be on top? We are going to generate more volume of water that we need to dispose of it, okay? We're making, I mean, as we urbanize, right, the volume of water is going to be higher, and the amount of water that is going to be collected at one point is not just going to be higher, but also is going to get there sooner. Okay, so there are two things that we're going here. Urbanization, okay, that goes through that. So this is the big picture that happens, right? And we need to address, okay, the quantity of water. When we have a new urban area that's being developed, we have to address the quantity of water that that area is developing. And also we got to go through some initial water treatment. And you will say, okay, what is stormwater? What those type of treatment are we going to use? Well, that's stormwater is having usually, you have oils from cars, you have total suspended solids that are coming from the runoff, okay, for erosion, of soil erosion. We have silts, we can have clays, we can have sand there as well. So those are the total suspended solids. But also we can have nutrients. Okay, where do those nutrients come from? Well, here we're talking basically about phosphorus, nitrogen, right? Most of us, when we got our house, now that spring is coming, I think somebody promised that we were going to have spring. You want to have that grass all green and everything, so we usually get some nutrients in those, okay? Phosphorus, nitrogen, and what's happening when it rains? Well, that water is going to take most of that with it as well, okay? So that can happen, and that's one of the causes for eutrophication, which is the over-enrichment in water bodies of algae or any other algae that we can have in there, okay? So it's over-enriching, and that is one of the items that, the issues that can happen, all right? Basically what we're doing is providing more food, all right, to the species that are in there, and that's going to affect the ecosystem, that microsystem that is going to be in there, okay? So there are things that happen. So how can pervious concrete pavement system help us in reducing the nutrients that can be deposited in the water bodies? Well, this is conventional concrete, okay? One thing with conventional concrete is we proportion our mixer, so the water does not penetrate the concrete. We don't want the water penetrating the concrete, okay? Pervious is completely opposite. We want that water to go through the pavement, to go through the concrete, okay? And then we want that water to leave our system. Now, this concrete that we use it, we don't have rebar in there. We don't have reinforced, steel reinforcement in there, okay? The primary benefits that we got, we're going to reduce the quantity of stormwater. Okay? We're going to basically absorb, collect the water that is falling, okay? We're also going to capture the first flush of the rain, which usually is the one that has more of the contaminants, more of the nutrients, more of the total suspended solid, okay? And also we're going to maintain this base flow, all right, of the water that we can. You got other benefits for pervious concrete, okay? Road noise, heat island effect, proof, skid resistant, and also the road spray. And most of the time we're going to use it, well, when I recommend us to use it, it's in parking lots, okay? Because we have a big area that can collect a lot of water, and we might not have any problems with clogging or sedimentation, okay? So pervious, parking lots is the main topic here. So how does it work? We got our underlying soil. We can or not have an aggregate base, okay? And then we have our pervious concrete. So we may have a sand filter, and think about this as a pavement, okay? Think of this as your car is going to be on top of that. So you're going to have the water that is coming on top of the pavement from adjacent sides. It's going to penetrate the concrete, okay? It's going to storage, and then the soil will take care in removing that water. So the governing factor that will design, that will rule our design is going to be the underlying soil. Okay, the permeability of the water that goes through here, we're talking about at least 300 inches per hour. Now you say, okay, so it's good, is it bad? Well, one of the best soils that we can have is 1 inch per hour. So we got 2 orders of magnitude here. So it's the underlying soil that will rule or govern our design. This is what it looks like in fresh state. Okay, the materials are the same. Okay, that you will use with conventional concrete. Just going to alter the composition of the coarse aggregate. You're going to have smaller aggregate, and you're not going to use any sand or very low amount of sand. That is what it makes the water go through the concrete. We basically are not using sand in the concrete. Okay, but everything else are going to have the same materials, and here we're looking into 2 properties. Okay, you say concrete, you say strength, durability, but for pervious concrete, we got into what I call the hydrological properties, which is porosity. How much water can we collect? How much water we can storage? And that's going to govern our design as well. Okay, and the other is the permeability. Okay, we got water, how fast the water can go through that. If you're into soils, you're going to say, well, this is factor K, which is hydraulic connectivity. We call it permeability for pervious concrete. Okay, and minimum for pervious concrete, we're talking about 20 inches per hour. Okay, to put that in comparison, 1 inch per hour for a soil, it's really high. But we can even have 2,900 inches per hour of water that just goes through that. So it's very fast. So what it is that we're doing? Well, what we're doing is determine, okay, the quantity of nutrients. And by nutrients, I'm talking about phosphorus and nitrogen that pervious concrete can remove by having the water go through that. Now, we are adding a couple of components to the concrete, of ingredients, if you want to say, to that, which are, one is iron fillings, and the other is wolostonate. Iron fillings is just iron, okay, very fine iron, not as fine as sand, okay? But what we do is we substitute by weight a percentage of coarse aggregate with the iron filling, right? And see how much phosphorus and how much nutrients we can have. And the other one that we're looking at is wolostonite. Okay, that's a mineral. It has calcium in it as well, just as cement. So we're looking to see how we're adding this to a concrete mixture, how much nutrients we can remove, right? And also, but here's the thing, here we are altering the properties of our pervious concrete. And most likely what we're going to affect is the porosity and also the permeability, right? Which are the 2 hydrological effects that we'll have. So what some preliminary results, we did some tests with phosphorus, okay? And what we did was proportion a mixture that's normal pervious concrete mixture. Then we substitute 5% of the coarse aggregate with 5% of iron fillings. We do the same with the 7 and 9% substitution. Now the permeability, okay, that we have for control was 1,500 inches per hour. Okay, generally speaking. The 500, as we expected, the permeability was reduced to less than half of that. For 7%, it was a little higher, but it was reduced as well. For the 9%, it was almost the same as control. Why was that? It's most likely that's going to be the mixture procedure. Okay, pervious concrete you need more quality control. So the mixture, how we mix the mixture, and that's it's a good terminology, right? It's going to depend on the final properties that you will have. For porosity, which is the voids that is going to have interconnected voids, we're talking to 20%. We reduce that to 13%, and that's going to affect the design as well. 13% to 7% reduction in porosity, and 20%. I'm sorry, not the reduction. This is the overall porosity that we'll have. So for this one, didn't show any reduction in porosity, but again, we are looking into those. So the way that we test, okay, basically what we do was we run in a uniaxial test. What we did was have the water, okay, go through the concrete. Okay, uniaxial test, so we can determine here the rate at which water goes through the concrete, and we can take the time of contact between the water and between the concrete, because that is one of the things that is going to affect. So we run it in a couple of ways. We used in two flows. Okay, the flows, one was around 1 inch per hour more or less, and the other was just free flow. We just let the water go through that. Okay, the results that we had for those, the flow rate of, 0.1 inch per hour. This is the control, 5% substitution, and so on. Control didn't reduce much, very significant. 5%, 10%, 7%, reduced around 12%, and 9% of substitution got about 35% of reduction in phosphorus. Right? Running the water, this was around 30 minutes of contact between the water and the specimen. Let the water go through just freely. This was a great reduction. Okay, for 5%, for 7%, and also for 9%. Okay, that was reduced a lot. So contact time is one of the things that is affecting this. So what it is that we're doing right now? Well, we're developing our research matrix, developing the concrete mixtures, how much percentage of wolfenite we're going to use, iron peelings, and so on. Also determining what we want to do, what we're doing is having the relation between the nutrients and the quantity of these supplementary materials, the wolfenite and the iron, also the time of contact. Okay, we see that it does affect. Now we're going to see how much, right? And also effective life of, I don't want to call it durability, okay? Because this is effective life of, okay, we're going to run many repetitions with water, with nutrients, and then after 100 or after, let's see what it is that we got. Okay, let's see if we can still collect the nutrients at that point. And we are running a couple other tests. We're also using the environmental scanning electron before, during, and after to see what it is that we are getting into these specimens, okay? And this is a PhD student. Haytham didn't want to present, but he'll present next year for sure, okay? We'll likely have this, that's the plan. Nicole Villeneuve from Natural Science is helping us a lot in the chemistry department, okay? Testing phosphorus and how to determine the phosphorus and nitrogen contents and so on. Steve Grant, okay, that's this also, oh, I'm sorry, undergraduate student, well, Don Carpenter has helped us as well, and undergraduate student, Don, he worked with us, graduated. Oh my God, all right. Anyway, thank you very much. If you have any questions, Alan Kilwell, I'm sorry. Alan will kill me. Alan, don't kill me if you see this. Yes, Alan helped us a lot in the preliminary results. Okay. All right. Thank you very much, and I think everyone.
Okay, everybody. Thank you for coming today. I don't think I have the enthusiasm that Dr. Mata has this morning, unfortunately, so I brought some props. Hopefully that'll spice things up a little bit.
Well, congratulations with a new baby boy. 1 week old.
So I had my research engineer who I'd like to acknowledge here as well, Neil Baraska, come to the lab and pick up some specimens so I can show them to you today, get a feel of things. This project and a couple other projects we're working on right now are sponsored by the Tank Automotive Research and Development Engineering Center. And I've been working on these projects pretty much since I started, or some of them have evolved with Dr. Nabil Grace. One that we just completed was the one that was investigating the material properties of composite materials, which are these shown today. So for the inaugural research day, I thought it would be good to start with the one that's completed, and then preferably in the future I could show you some other projects that we're working on. And I pushed the wrong button. There we go. All right, so this project was funded, like I already mentioned, was funded by TARDEC, and the idea of using these composite materials in the Army ground vehicles is to reduce the weight primarily. That saves on fuel, and it also saves on general transportation of the vehicles, and that's you hear quite a bit about it if you're familiar with some of the what the Army is doing. Let's reduce the weight of the vehicles. All right, so these composite materials are being studied actually through some of the research projects we're doing, and we're doing components, but they are used for both ballistic protection and for interior components. The primary research objective of this study is to determine the complete three-dimensional material properties of the materials when they're loaded in shear, in compression, and in tension. And it looks like everybody in the room is an engineer. It seems like it, so I assume I'm going to present this like you somewhat know what I'm talking about, which is definitely helpful. We all had mechanics of materials, hopefully, at some point in our lives. All right, so here are the different materials that we've tested. A lot of the materials were reinforced with S2 glass fibers, and there was variations of resin. There was only actually 2 resin systems that we used for the epoxy. We had API SC15 epoxy, and we also had Huntsman Rencast 6405. And I went to the SAMP, I don't remember what the acronym stands for exactly, but a lot of the research that's being done through the Army for these materials is on this API SC15, or with that, this combination right here. But they also asked us to perform this combination. This is the combination with, again, a similar resin, but with material that was developed by Dr. Grace here at the university and patented by him. That stands for the ductile hybrid fabric. So that's the fiber system that's in this material right here. The last one they had us test was kind of a late arrival of the material. That was prefabricated a composite system with S2 glass and also armored fibers along the thickness of the specimen as well. So unique material there. So what we were doing is we weren't just doing the traditional test of taking our specimen here and pulling along the orientation or the axis of the fibers. Some of the testing we were doing was also through the thickness, and that's what these smaller specimens here are used for. For instance, this is an out-of-plane tension specimen, and we did some out-of-plane shear, or, you know, well, the word's slipping my mind, but we're testing shear through the laminates, and also we're subjecting them to compression. So that's where some of the unique tests came into play, and with each of these different materials, even when we thought we had a test procedure figured out using this material, it always changed because they all performed differently. And some of them did not perform well under higher temperatures. This is the matrix, or the test matrix, the 7 different tests that we had to perform to measure both all the elastic properties and also all of the strength properties. So one of the elastic properties that we considered was even the Poisson's ratio, which had to be its own separate test. Okay? Again, assuming you all know kind of what I'm showing here, I have shear properties, shear modulus, elastic properties in both tension, and these is the elastic modulus and compression, which is shockingly a lot different for these composite materials, which I just didn't know until I got into this research. Here's a lot of the ASTM references that we followed. Note that there was not an existing ASTM standard for a couple of the tests that we had to perform. So therefore, we had to develop our own testing method to measure those material properties. Another obstacle in our research was the fact that we were testing at cold and hot temperatures. So we tested at as low as -40 degrees in these environmental chambers and as high as 140 degrees Fahrenheit. And these were the ultimate worst case extremes that we with Tardik decided upon. And of course we did test at ambient as well. So not only did we have to run the test, but we had to accommodate testing within these environmental chambers. So we had to cut holes, or we had holes top and bottom. We had to slide our attachments, our threaded rods through the chambers and have test setups inside the chambers. Now, I'd like to just kind of go through some of the different tests that we ran. I'm trying not to focus on the results here because there's a lot of them. But so here is the more classic, traditional out-of-plane tension, or in-plane, sorry, tension test in the plane of the fibers. So there's well, anyway, I'll just show you with the specimens that I brought. So we're subjecting them to tension using the Instron test machine here. And we had strain gauges, of course, located on the specimen to measure the elastic modulus and the Poisson's ratio when subjected to tension. Every now and again you had a specimen like the DHF that had a unique failure mechanism which caused modifications to the specimens. If you can see, this one was actually spooled down a little bit, or has a reduced gauge length right here, and that was necessary because of that localized failure mode. So we had to control the thickness of the specimen along the length. Other ones, the ones that we were originally testing, had delamination along the length, so it wasn't that necessary, but you can see the complexity each time we do a material and a test, we had to reinvent the wheel, it seemed like. So, I don't know if I said that right. Is that the classic line? Okay, all right. So here is, this one. Here's the compression test. The compression test was done on the MTS machine, and it needed some special fixtures to avoid buckling of the specimen, so we can test it in pure compression. We had to really fit some strain gauges on the test, make sure we can get strain gauges in there and monitor them. This is the dimensions of the specimen and different failure mechanisms, and I would spend too much time talking about each of these slides if I don't move on. Here's the shear specimen, that's also known as the bow tie specimen, where the specimen is gripped on one side and gripped on the other. I think it's the top that remains fixed, and you pull down on the bottom such that you shear the specimen like this. And we're measuring what happens in the reduced gauge length right here. And we have a strain gauge attached directly at that spot. So we're measuring the shear modulus using these strain gauges, and of course the shear strength. Not too much of an exciting of a failure mode, but I mean, you can see when the failure occurs, you can see a little bit of a fracture right there through the strain gauge. Okay. Now, for those three tests, they performed pretty well, and we could use regular ASTM standards, but one of the main variables in our research was the nominal material thickness when it was fabricated, and that ranged from 0.75 inches to 1.5 inches. And that caused a problem with these out-of-plane tests because we had to grip the specimen top and bottom. Yes?
No, you got 5?
Oh, okay. We had to grip the specimen. Am I the short one because I'm last though?
No, I'm trying not to.
Oh, okay. All right, so if we grip the specimen top and bottom, it's very difficult to do so. So what we had to do is put on attachments. So for instance, if this is the specimen that's tested along the thickness, then we put on what we call the end tabs, top and bottom. And we would epoxy them to the specimen. This idea was all generated here at LTU in order for us to test this material within the center. So there's a lot of efforts here. First of all, they're epoxied together and clamped, which is shown over here. And then they were all grinded down and squared, which is shown here, using this custom electroplated diamond-coated wheels. And a lot of this work was done by Neil. I wish we actually stuck around so I could acknowledge them better. And then the individual specimens were made by using a bandsaw and cutting them into individual lengths of, I believe, 1 1/8 inches. And then in order to attach them to our test fixture, we drilled holes top and bottom. Okay, and they're actually, you can see them on this specimen here as well, little holes for the out-of-plane specimens. For the tension specimens, not for the Poisson specimens, we had to grind them down even more to create a circular cross-section. And the hardest part was to ensure that we had failure in the test area and not at this black line, which is the epoxy bond between the end tab material and the material tested. So this is a 0.75 inch thickness, so you can kind of get an idea of why we had to do all this work in order to make sure we're testing within the material that we're actually physically testing. So it was kind of difficult. Here are some of the finished specimens. These are tension specimens, these are Poisson specimens. So each time we had a different specimen, we had to come up with this unique shape. It happened every single time because the one we were just using isn't working. So we had to change it up quite a bit as we went along here. For the shear specimens, this is kind of how we developed the, I haven't actually shown you the small shear specimen. I've only shown you a big one. I'll show you that test in just a second. But for the small shear specimen, we had to develop these V notches top and bottom, and we did that with a, what's the name of it, a Bridgeport mill with a machine. We put it on a Bridgeport mill to machine the V notch all the way through, and then we cut them into individual specimens. Okay, I got 3 minutes. All right. So here's the out-of-plane tension test that's performed on the Instron. This is it zoomed in and connected to our fixture, so we're just pulling on these specimens at tension and measuring elastic properties with strain gauges. Here is the out-of-plane shear test, which is a much smaller specimen, like I said, that needed the end tabs as well. This is the in-plane shear test. The out-of-plane shear test is very, very small through the laminates here. So here's a close-up of that test. Idea is the same. We're holding the bottom fixed and we're pushing down right here. You can see how this rod comes down and pushes on top of the fixture. That creates shear in this region. Finally, the Poisson test is very similar to the out-of-plane test, but it needs to be a square specimen because we know what Poisson is. It's the lateral strain over the longitudinal strain. So we need a nice square specimen to perform that test. A bunch of results. Won't have time to go through them, but to give you an idea of what we were, in the end, we had to analyze all this data. For each of these results, 5 specimens were tested. For each test type, for each material, and for each temperature. That represents 5 data collections, or 5 specimens. So we got a whole bunch of data in the end. That's 3 materials, we had 8 overall. Here are some of the trends of what this is the result at a particular temperature divided by the result at ambient. Okay, so it's normalized to the results at ambient. You can see how temperature influences the in-plane tensile strength and how it influences the in-plane compression strength. Okay. They didn't seem to do this for everybody else. Interesting, what comes out of it is that, I'll make one note, that was a consistent result, is that the materials that had this epoxy, Huntsman, Redcast 6405, performed much worse at higher temperatures than the materials with API SC15. So all these were API SC15, these were all Huntsman epoxy, Redcast 6405, same thing there and there. And even though it performed better at cold, we still felt that because it's worse at hot, that's probably, you want things to be as close to ambient as possible. So we thought that was good. Okay, the materials themselves, we did comparisons, and we found with ductile hybrid fabric, we had the most stiffness, but not necessarily the most strength. And this is it, this is my last slide. I had about 4 pages of conclusions. I've condensed them down into this here. But, so, the materials with API, SC15 epoxy, and S2 glass usually have the highest in-plane and out-of-plane strength results. And the materials with ductile hybrid fabric, the ones, like I said, that were patented at LTU, or that material, that always had the highest stiffness because of the ultra-high performance concrete. Ultra-high performance carbon fibers, or ultra-high modulus carbon fibers. Yeah. Not just high, but ultra-high performance. Okay. So the properties, the strength properties decrease with an increase in temperature. The stiffness usually decreases with an increase in temperature as well. And the strength and stiffness results of Huntsman PU Raincast 6405 are definitely more influenced by temperature than materials with API SC15 epoxy. And overall, the out-plane Poisson's ratios of these materials are all over the place, regardless of properties. They're usually between 0.1 and 0.3, but there's really no trend in any data that we found in Poisson's ratio, just in the rest of the properties. Knowledge, Dardic, they've been supporting us for a while now, and of course they do a lot of work with us over in Simmer and Edson. All right.
Thank you very much.